water quality in the field isn't terribly exciting. It's really just taking a probe out there and measuring it. And the most important thing about water quality is how calibrated your instrument is, how accurate the numbers you're going to get out of those instruments are. Because if your instrument isn't calibrated, you're getting junk. It doesn't tell you anything. I did grab 3 mystery water samples. I'll put a list of what those mystery options are on the board. And I got an aquarium test kit which analyzes, so it's a titration analysis, which you guys all should know what is from your reading assignment. Do it for pH, ammonia, nitrate, and nitrite. And unfortunately, the nitrate sampler on our sonde doesn't work, so we thought we were going to try and cross-check and see which one appeared more accurate, but it's the way of the world. But hopefully there are some differences, and we'll also use the sonde to look for differences in conductivity. We're not so much going to be interested in dissolved oxygen in these samples because I just have them in a bottle. Typically dissolved oxygen is something you measure in the field on site, as would be water temperature and some of site-specific parameters. But we will do a calibration of dissolved oxygen here in the lab and try and get you guys familiar with some of the equipment and some of the terms that typically go along with water quality. So this is a much smaller wave than it looks like in Maui. All right. So the first thing I wanted to chat about are dissolved gases. So when we're thinking of water quality, some of the most important components are those gases in the water because biology is either producing them or consuming them. So the big ones that you're generally thinking about are CO2 and oxygen. And let's first think about where oxygen is coming from. So in an aquatic system, you're going to have atmospheric mixing. And that's going to, regardless of whether you have any biology going on at all, this mixing by wind, waves, currents is going to dissolve atmospheric oxygen into the water. And the atmospheric pressure, the partial pressure of oxygen in the atmosphere, is going to drive the concentration of oxygen in your water. You guys all read in the assignment, and I think had a question on it, what is one of the main drivers of the amount of oxygen that's going to be in the water that I haven't talked about yet? Temperature. Temperature. So water temperature is going to dictate how well gases dissolve in the water. If the water was really warm, would you expect there to be more or less than when it's really cold for oxygen? Less when it's warm. So the gas molecules are moving around more quickly. So they're leaving. Gotcha. So cold water. So when you think of, say, animal species like fish, so trout really need cold oxygenated water, and that really ties together the cold and the oxygenated are what sort of drive what they need. But then there's other species that can tolerate warmer water. They can often also tolerate much lower dissolved oxygen. And that's because you're going to have lower dissolved oxygen in water. Okay. So then in terms of the biology, you're going to have photosynthesis. And photosynthesis could be both macrophytes that we talked about in one of the previous lectures, as well as phytoplankton that are going to be producing oxygen in the water. Then you're going to have consumption of that oxygen. You're going to have respiration, and everything that lives respires. So that's going to be consuming that oxygen. You also have decay. It's still respiration, but basically things that are breathing are consuming. Photosynthesizers also respire, and remember that was that balance between net and gross primary production. But the decay of stuff on the bottom is also going to be consuming a bunch of oxygen. Those are most of the things. And so here's the graph that actually is showing you the solubility of oxygen in water as related to temperature. so much, much less soluble at water temperature. CO2 is also being produced via respiration, but primary production is grabbing that CO2 out of the water column and using it with sunlight to make food and then producing oxygen. So you've got energy from the sun, water, CO2, food, and then producing oxygen. So when we're generally thinking about things that are dissolved in the water, we're thinking about ions. One of the measures that you'll often see referred to when we're talking about water quality is TDS, total dissolved solids. And really that's functionally the concentration, the sum of these major dissolved ions. And the major ions are sodium, potassium, calcium, magnesium, and then bicarbonate, carbonate, sulfate, and chloride. Typically, this is getting measured by evaporation. So you're basically filtering out a bunch of water, and you're weighing how much residue is remaining, and that's going to be your total dissolved solids. Now, there are many other ions that are present in the water, but generally from a sort of numerical mass perspective, they don't make that much of a difference. Nitrogen and phosphorus and iron are very biologically important, but they're typically not making up a big component of your total dissolved solids. Each of these ions have a different source in the environment, and we'll go through some of those sources. But the major ions, typically in flowing water systems, are bicarbonate, sulfate, and chloride, and they're associated with the weathering of sedimentary rocks. So if you think about the geology of a watershed, what the geology of the watershed is going to have a very big contribution to the water coming out of it. So if you had an island volcanic system, you're going to have very different water chemistry than you are in a sedimentary area like, say, Ventura County. Another measurement that we're often interested in, is conductivity, and that's really looking at just the electrical conductance ability of the water. Now, sometimes you can measure total dissolved solids basically as a function of this electrical conductance. There's usually a linear relationship, but it's often a sort of site-specific, water chemistry-specific relationship. This is the unit that you'll often see, and so when we're looking at the SOND, the water quality SOND, you'll see units of microsiemens per centimeter. And the centimeter part is basically looking at the space between the cathode and the anode of the sensor. So it's looking at the measurement of the electrical transfer between those two divided by the size, the spacing between them. Because if you had a sensor with one space this wide versus this wide, you're going to get a different conductance. So and that's typically called specific conductivity.
Would that be the constant? The centimeter, the distance in between the anode and cathode?
So that's what you typically would not report conductivity. You would typically report specific conductance because that makes it comparable. All right. So our major dissolved constituents, calcium. Calcium is generally the most abundant cation, and it's coming from rock weathering. When you hear people talk about like hard water is really the concentration of calcium combined with the concentration of magnesium, and that's what generally causes the formation of insoluble compounds, like when you have soap. Like when you're using hard water, like the soap will form these crusts. And so it's not interchangeable necessarily with alkalinity. And we'll talk a little bit about that in a second. Sodium is generally associated with chloride. And so NaCl, you guys, regular table salt. It's generally coming from rock weathering, but when you think about systems adjacent to the ocean, you have enough salts getting resuspended into the atmosphere that you also get salt also coming in your rain, at least adjacent to the ocean. But salts are also coming in from human impacts, and not so much here, but certainly the Midwest and East Coast, road salt can be a major contributor to the amount of salt. And it's not always sodium chloride, but you can have, I don't remember what the other road salt is, but it has sodium. Sewage often has high concentrations of sodium, and then fertilizers often do as well. Bicarbonate is coming from the weathering of minerals, but also the decomposition of organic matter, and we'll talk about the bicarbonate buffer system in a little bit, because bicarbonate is very important in aquatic systems. Sulfate is coming from rock weathering, but it's also a major component of fertilizers. It's often found in waste coming off of mining operations, and it's produced by the combustion of fossil fuels. A more unusual, and I think depending on how much volcanic activity is happening, but volcanic activity can also result in sulfate. And you guys all know that pH is really the measurement of the amount of hydrogen ions present in the water. So from a ecological standpoint, we often are thinking about what's the load of a particular constituent that we're interested in. And when we're thinking of the load in terms of, say, a flowing water, it's the concentration of that constituent multiplied by the discharge of that aquatic system. So that's giving you some rate per unit time of your constituent being present in the system. Now, the U.S. Clean Water Act, from more of an environmental science perspective, has developed for impaired waterways these things called total maximum daily loads, or TMDLs. And that's the amount of pollutant that a body of water can receive while it's still meeting sort of set water quality standards. And so you often will see, particularly urbanized watersheds, but anywhere where there's substantial human impacts, total maximum daily loads that get established after people discovered that the waterway appears to be impaired. The TMDL is the sum of a point source, so a waste load allocation, the load allocations of these non-point sources, so the diffuse sources from the environment in the background of that aquatic system, because often some of these constituents are naturally present in the water, but the increase in the concentration is a result of human activity. And then this is sort of where we're stepping into sort of policy, is what do we consider to be the margin of safety? Like how much of an increase would still be okay, knowing that probably there's variation in the load over time? What would you never want it to exceed? So what's that margin of safety? Okay. Yeah.
So for TMDLs, are those are determined and set, and then you do your measurements against that?
Usually, so for example, the Santa Clara River has TMDLs for chloride, and that's a result of major wastewater inputs from LA County, so Santa Clarita, Valencia, all those. Basically, you're in a really arid area, you have a lot of evaporation going on and a lot of people. You have lots of, in the wastewater, lots of chloride also coming out. And so they have to do they have TMDLs for how much chloride they can actually be.
So you wouldn't go out and measure a TMDL
You would measure water quality constituents and
compare them to that.
and
TMDL
compare them
see
to
if
that.
they're-
Yeah, if you're
Within
meeting your standards.
Yeah, okay.
So that's set by the government, right?
Yeah, generally, and government is that's a very vague term. It could be a regional water quality control board. It could be the U.S. EPA. It depends on who has jurisdiction over the waterway. I think in Santa Clarita it's the regional water quality control board, but there's also the state water quality control board, and they all have their own standards. And the standards can be site specific. You know, there's sort of a general guideline for what you shouldn't have, but then there's also systems where you have naturally higher than, say, those TMDLs. So it wouldn't, like, you couldn't expect someone to meet a TMDL if the natural concentrations were higher than the TMDL. So it's sort of that political process as well. Yes.
Is there consequences for, like,
That's sort of
Yeah,
getting
like-
beyond my experience, but my impression is yes. What exactly those concentrations, or no, sorry, whatever those consequences are,
and who would
depends
be
on who's the
responsible?
enforcer.
Would United be responsible for Santa Clara? Like, if there was
No.
a problem, or would it be the people?
United is one of the people who have sued against the folks that are delivering lots of chloride-rich water
Gotcha.
into the Santa Clara River system. So chlorides are a major concern for groundwater management. So we don't want a bunch of chloride coming in.
How dynamic are these TMDLs? Like, for Santa Clara River, will it change seasonally?
That I don't know.
To, like,
I believe it's not seasonal. I believe it's sort of a set, and that's sort of where that margin of safety is coming in.
okay.
So the landfill had to implement best management practices for stormwater issues like this. And so we had to, after every significant rain event, so if you could visibly see rain on the ground, you had to go measure water quality. And we obviously didn't do the testing there, but that is through this TMDL load to make sure our runoff isn't affecting the waterways.
Gotcha.
And so it just depends. Like a landfill obviously is going to have higher levels of chemicals and
this,
all
yeah.
of it stuff, but we were really concerned about total dissolved solids, and our turbidity was really high and it was causing a lot of problems. But we also had a park next to us, so there was a lot of issues with it. So we never passed. We were always in trouble, and so we always had to change our DMPs and try to adjust how to make our water quality.
Do you guys know what BMPs are?
Best management practices.
So one thing that Emily alluded to that I wanted to also point out is, say you're a consultant working on water quality, you are probably not going to be the person actually measuring the water quality. You're going to be the person going and collecting a sample and then shipping it off to an analytical lab. However, on the alternative side, if you were, say, a graduate student interested in water quality or an undergraduate student interested in water quality, you probably would need to learn the chemical techniques to actually do those analyses. And I sort of apologize for the Brouwer chapter because it's talking very explicitly about how to do those analyses. I wanted you to sort of get the broad strokes, but not so much the specifics of those analyses. But that being said, you may decide to pursue an academic career or at least higher education, and you might not be able to have enough money to go and have a lab process your sample at $10 a sample, when you could process it yourself and do it for 25 cents a sample. So there's sort of our water quality lab today is going to be focused more on the calibration side of things, and we're going to do a little bit of titration because a lot of the more accurate methods for doing some of these quantifications require a lot of either toxic chemicals or very specific lab setups for those particular analyses. And you also have to think about chains of custody for, well, how did you treat your sample in between you collecting it and bringing it to the lab? Something's going to break down in the process. Like if you have bacteria in your water, you could have transformations, and we'll talk a little bit about them in the nitrogen cycle. And so you generally have to either do some sort of preservative immediately, depending on the analysis, or you have to keep it on ice, or like filter it immediately. There's different ones for each different constituent, and so you often say you wanted to analyze like 10 different constituents, you might have to collect 10 separate bottles and maybe replicates of those. The other thing that Emily brought up that I thought was pretty interesting is thinking about stormwater and sort of these short inputs into aquatic systems. You often will have water quality management projects, like Ventura County, the stormwater program goes out and tries to measure water quality at all those peak storm events at a number of target locations. If you're doing a construction project, you often have to have best management practices in place, and then you have to ensure that you're in compliance with those by going and collecting water quality information. And so often when you see, like, say a construction site and they've got those black fences around them and those swales of hay, that's all to contain water in the site and to contain dust and runoff from the site, basically to maintain water quality. Okay, now let's talk about the phosphorus cycle. Phosphorus is an essential nutrient. It is a major component of many, many key molecules that are important for biology, most importantly ATP, where you get your energy. But phosphorus isn't actually all that abundant in the biosphere, and even where it is, say, fairly abundant, it's not really in a bioavailable form. And so this is a very big distinction from nitrogen. Phosphorus is coming from weathering. So you have weathering of sedimentary rocks, you have transport of that via wind or water. In the soils, there's some subset of phosphorus that's available in an inorganic form. It's going to be combined and used by biology and into an organic form of phosphorus. That those plants are going to die and then potentially be in the organic phosphorus pool in the soils. But eventually, that phosphorus is going to become unavailable, and it's going to end up in the ocean as an inorganic, in the sediment, and then eventually, over very grand time periods, the sediments are going to be uplifted, and then the process starts all over. So when we think of phosphorus, it's really important to consider where's the source coming from, and what are those consequences for when we're consuming phosphorus, and where is it going? Nitrogen cycle, conversely, has a number of different forms. Nitrogen is the most common gas in our atmosphere. And so let's first think about nitrogen becoming a bioavailable. So you've got lightning fixation. So lightning can basically strike the nitrogen molecules and convert it to an available form. Bacteria can also transform it. We apply fertilizers in a lot of situations. And so you're getting nitrogen coming into organic matter, and it's usually complexed with some sort of carbon molecule. So when you urinate, you're excreting urea. And so that then gets mineralized into ammonium, which gets nitrified into nitrites, nitrified into nitrates. Nitrites aren't really available for biology. Ammonium is. Nitrates are. So those can get consumed by plants. But all of these can be leached out of the soil, out into aquatic systems. They can also get denitrified and be transformed into nitrogen gas. Bacteria are really important in the nitrogen cycle. You have some that can fix nitrogen, so basically taking it from gaseous nitrogen into a bioavailable form. You can have them converting ammonia to nitrites and to nitrates, and then converting it back into gas. So let's go to an aquatic system. Let's think really simply about an aquarium and the nitrogen cycle in your aquarium. So you're putting in nitrogen in your food. Fish, unlike humans, excrete as ammonium. That ammonium then can be transformed into nitrites by bacteria, and then transformed into nitrates, which are then bioavailable to, say, you have aquatic plants in your aquarium. But the plants can also be decomposing and contributing ammonium into your water quality. So ammonium is toxic to your fish. So you generally need your nitrogen cycle to be functioning, otherwise your fish will die from their own waste. So it's generally sort of where the water changes come in, and why you need to have a biological filter in an aquarium. Okay. But we basically do some of these things on a grand scale. And what are the consequences of nutrient enrichment? So we are very deliberately enriching nutrients in the environment because it helps us grow our plants. The entirety of the Mississippi River drainage has massive fertilizer inputs. And that has caused major consequences for the Gulf of Mexico. So you have all these high nutrient loads coming out into the Gulf of Mexico, translating into high primary production of algae, and then those algae dying. And that decomposition consuming oxygen and making these hypoxic zones, so these really low oxygen zones that basically can kill off or make animals move out of those areas.
I thought it was that the areas would become over-oxygenated and then animals wouldn't be able to live there. Is that? Oh, okay.
No, so you can, there are some problems with over-oxygenation, but it's generally lack of oxygen that's the problem. So the primary production then has consequences for basically lots and lots of biomass then falling to the bottom and getting consumed and then consuming oxygen. But I wanted to throw a little additional concept at you, environmental stoichiometry. So I said, okay, we add fertilizer to a system, it translates into lots of production. However, from a sort of more conceptual perspective, and this has become a pretty active field of ecological research, is thinking about the imbalance between what you are and what you eat. So you have a particular elemental composition. What you eat has a particular elemental composition. And the difference between that is basically how much of it you need to eat to be able to translate food into your body tissue. So we typically are thinking, when we think of stoichiometry in the sort of ecological environmental standpoint, as being the ratio of carbon to nitrogen to phosphorus in your food. It's been extended to really sort of any nutrient or micronutrient, but often the big drivers, carbon, nitrogen, and phosphorus. One of the first observations of this was in the ocean by an ocean scientist named Redfield, and he observed that in the ocean, it was pretty consistent in all the world's oceans, that there was a ratio of 106 to 16 to 1 in plankton, as well as in the water. And he was interested in which one's driving what's going on. And it appears that biology may be what's driving the sort of general composition and sort of both of the time frames in which the nutrients are produced in the atmosphere or in the environment. So remember, phosphorus is sort of a one-way ticket from weathering through biology and then eventually settling out in the bottom and getting into sediment, where nitrogen can be resupplied in the environment. So you can see there's a lot more nitrogen typically present in the environment than there is phosphorus. Now, when you have imbalances between what you are and what you eat, that can change your feeding rates or your behavioral strategies. It can change the growth potential. So remember when we were thinking about algae and algal production in a stream, I said nutrients are really important, and nutrients can contribute to how much production you have. Well, it depends on what nutrients limiting. So it's those rate limiting aspects. You could keep on adding nitrogen, but if nitrogen is no longer limiting, you are not going to get an increase in production. At some point, you have more than enough nitrogen, and now phosphorus is limiting. So maybe then you need to add more phosphorus. And so it's those ratios between the different constituent elements that are going to tell you, okay, if you're a farmer and you're applying fertilizer, probably at some point you don't need to add more nitrogen, you need to add some phosphorus if you want to get more production. All right, now we're going to shift gears entirely to the bicarbonate buffer system. So in the environment, you have lots of CO2, right? And when it gets dissolved into water, it gets transformed into different forms depending on what the pH is. And dissolved carbon dioxide reacts with water to form carbonic acid below pH of 8. Bicarbonate and carbonate react with water to form hydroxyls, so these negative ions. When you, say, add some acid to a system, you're going to start neutralizing. So remember, acids are positive charge because it's a hydrogen ion, acid. When you add some acid, these hydroxyls are going to be neutralized, but you're going to continue to have more and more form until you've exhausted your carbonate supply. So basically, you can add some acid to a system, and this buffer system of carbonate bicarbonate will slow the change until you've used up the carbonate, and then there'll be a rapid change in the acidity of your water. So this is important because rain is usually acidic, and it's acidic because it's coming through the atmosphere where there's tons of CO2, and there's also naturally occurring sulfate up in the atmosphere. When rain hits the ground, it typically becomes neutralized up to the buffering capacity, so how much carbonates are available in the geology. When we burn fossil fuels, we put sulfate and into the atmosphere, and that causes atmospheric acid precipitation. And depending on what the geology of your soils are, you may exceed the buffering capacity and then have a rapid change in the pH of your aquatic systems. And so again, it all sort of ties back to the geology of your system. If you had a volcanic system that has very little buffering capacity, then acid rain falling there is going to immediately change what's going on with the pH of the stream. But in a stream that has lots of carbonate rocks, it's not going to change very quickly, but you're going to have a lot of weathering going on. So the textbook made the distinction between hardness and alkalinity, even though they both are being presented as milligrams per liter of calcium carbonate. And the difference is sort of in a functional sense that alkalinity is what's the capacity of the solute to neutralize the acid. So particularly from a groundwater perspective, I think somewhat about salinization of fresh water. And this is very common in arid and semi-arid areas. And one of the big drivers, so say think about farming in Arizona. You have agricultural irrigation going on. The water is going onto the ground and then it's evaporating. But it's leaving behind salts. The salts aren't evaporating. And they're becoming more and more concentrated. And those salts themselves, when you apply more water, can actually leach salts out of that are already in the soil. So that could cause major problems for both the aquatic systems as well as basically you often have to retire fields when you basically get too much salt accumulation there, or they need to do things like trying to rinse the salts out of the soil. We also see, I already talked about it a little bit, but road salt application can potentially be problematic. In terms of areas like Southern California, where we have aquifers that are extracted from all the way adjacent to the ocean, this also happens in like Monterey County, where there's a lot of ag close to the ocean, and also groundwater extraction close to the ocean. The interplay between where you're extracting the water and how much you extract may have salt water come in to those freshwater aquifers. Generally, the pressure would be from the high part off on land to the low part at sea level, but that's not always the case. But also think about if you go to like Death Valley and Badwater area, that's a basin that's completely collect all the water that falls in that basin ends in that basin and then it evaporates. So the Badwater area is crazy salty because all those salts are getting eroded from the mountains around and then ending up in this dead pool at the bottom. One thing that I also wanted to point out, though, is we often divert water out of rivers, and depending on the system, there may or may not be a typical form of what the water chemistry would be during the summertime. In some systems, there would be a disconnection from the salt water, and so you'd expect actually an estuary to be more fresh water during the summertime because there isn't very much salt exchange. And if we divert water from a river that's contributing water to the estuary, you may potentially increase and make it more brackish, which may not be as livable for depending on what species. But it all depends on the context and what those estuaries would have experienced prior to the water diversion. Now I know some of you guys were really excited about the idea of studying water pollution and understanding water pollution. So I wanted to point out some of the other things that people are interested in when we're thinking about water pollution. Arsenic and fluoride both are naturally occurring, particularly in groundwaters. Arsenic is often a result of mine waste and mine runoff in addition. They're both fluoride, yeah, you put it on your teeth, but at really high levels, it can be toxic. Arsenic is pretty much just always toxic. It's been less of a problem in the US, but certainly water systems throughout the world have major problems with pathogens, and often the transport of pathogens from, say, bathroom facilities into water supplies. And so typically the pathogens that we're concerned with in the water are from feces. But it can be bacteria, viruses. Helminths are little like wormy guys. Nitrate is applied as agricultural fertilizer, but also biological waste. So our wastewater is a big input of nitrate. Organic compounds. There's a number of different organic compounds. They typically are coming from industrial wastes, but also they're being applied as pesticides. You can also think of spills from, train spills or oil spills or whatever, contributing organic compounds to the environment. Heavy metals. The importance of heavy metals in an aquatic system is usually going to depend on the pH or the oxygen status of that, because most of these metals will become charged and then potentially biologically available. Metals can be naturally occurring, and in the Oxnard Plain we have aquifer segments that have high, I think it's manganese and iron, but that's just naturally in the sediments that make up that aquifer, but at certain concentrations those exceed drinking water standards. Industrial activities and waste disposal often are major contributors of metals. And I wanted to spend a little bit of time talking about pharmaceuticals, because one of the things you maybe hear about when we talk about recycled water or reuse of water is pharmaceuticals aren't necessarily something that always gets analyzed for, or that we even have ready analyses for. And so you go out and you measure the water quality for some particular set of parameters, you meet all of the standards for those, but you're not seeing everything, and you're not analyzing for everything, and considering what the consequences of some of the other components that you're not measuring might be, you may give a good water quality status to something that for other reasons isn't actually very good. So one example of this is environmental estrogens. So this is an example from England with a fish called a roach. It's in the carp family. And people started making the observation among wild roach populations downstream of a wastewater treatment plant. They would catch them, and they would have characteristics of both males and females. Their gonads would actually have both eggs and sperm in them, testicular and ovarian tissues. And within a fish, the typical pathway for production of this chemical called vitellogenin, which is a precursor to the yolk in an egg. So it's what after the egg is fertilized, what the animal is going to use for energy during early development. Typically, you only find this compound in females when they have estrogen stimulation. And so there's some environmental cues in the fish that are causing the brain and the pituitary to produce estrogen. Within the fish, you get vitellogenin going into the blood and being incorporated into the yolks of these eggs. But fish can also be getting estrogen from the environment, either through the skin or through the gills. And this is potentially what's causing these fish to become intersex. And in areas downstream of these wastewater treatment plants, you have much more of a prevalence of these intersex fish, and they typically have much less success in reproduction than fish without intersex characteristics. Now, I hear you guys talk about microplastics, so I figured I needed to chat about it a little bit. One of the first things that I found while reviewing the literature for this is microplastics is a pretty vague term, and people have used, even within the last 5 years, a number of different size classes when they're referring to microplastics. anywhere from something less than 10 millimeters to something less than 1 millimeter. And so one of the challenges, if you were, say, doing an analysis of microplastics and microplastics in the environment, is to make sure if you were comparing your data to some other study that you guys are using the same classification for plastics. Plastics have sort of two main sources. One is sort of a primary source, and that's microplastics that were made as miniature plastics, versus secondary plastics, which are larger pieces that are being broken down into smaller fragments. We know that they're ubiquitous in the marine environment, and people have been observing them basically since the production of plastics in the 40s. What makes them particularly important is that they're very bioavailable, particularly for filter feeding organisms, because they're so small, and they're of a size that those filter feeding organisms would already be consuming. What makes them particularly worrisome is that they can absorb waterborne contaminants, and so these can be like metals or hydrophobic compounds that you wouldn't otherwise be bioavailable, and then somebody consumes that microplastic, and now they have those metals or those hydrophobic compounds in them. Plastics generally are considered by themselves to be pretty much biologically inert, but components of the plastic making process that make plastics more plasticky, like they're actually called plasticizers, will degrade, and some of those additives are things like endocrine disruptors that could potentially be problematic for animals. One of the things I thought was most interesting, and I can provide you this review paper if you're interested, is they talk a little bit about biodegradable plastics, because that's sort of one of the new hot things. And so it's typically like a starch or a biological oil, but it's being combined with some sort of synthetic polymer. And so often these things will break down, but the synthetic polymers still won't break down. And these biodegradable components are biodegradable under particular contexts. So in the marine environment, where the water is typically cold, there aren't as many bacteria that can degrade them around. They may have a similar lifespan to a regular plastic. In industrial composting facility, where the conditions are much better, then you can have those break down more quickly. Okay. And particularly for you surfers out there, I wanted to talk a little bit about fecal coliform, because that's often one of the indicators you see about like beach health. And my wife is a microbiologist, and she's always commenting about this assay, because it doesn't necessarily mean that there's feces in the water. So basically, the coliform group are facultatively anaerobic, so they can live without oxygen. They have these particular components that identify them within this group, and this group includes things that are found in feces, particularly E. coli, which is the one that we're often using as an indicator, but there are non-fecal genera that are contained in this group. When people are reporting fecal coliform counts, they're actually doing an assay that doesn't distinguish between the fecal and the non-fecal, though that may change as techniques improve. You could potentially like even sequence and figure out things, but the current methods don't do that. And so basically, if there's interest, we could do a fecal coliform assay. It takes a couple days to grow, but we could do it if you guys are interested in it. But basically, you take a filtered water sample and you put it with lactose. and you incubate it at a particular temperature, and then you spread it on some agar, and then they basically just count the number of colonies, and knowing how much you sampled and how much you put on there, you can estimate a fecal coliform count. But I'd really call it a coliform count rather than necessarily a fecal. But it is a generally sort of good indication of what's going on. Alrighty, so those are the big things that I wanted to talk about in the lecture. And, you can stop there. So